Inside a large language model, meaning is a mess. Concepts get tangled together across the same neurons, packed so tightly that a single unit can fire for dozens of unrelated ideas at once. Researchers call this superposition, and it makes the network almost impossible to read directly. So how do you actually see what a model is representing? DeepMind's answer is Gemma Scope, an open suite of sparse autoencoders that pulls those tangled activations apart into clean, nameable features. Gemma Scope 2 extends that work to the Gemma 3 family, all the way up to the 27 billion parameter model. Let's open it up. So how does Gemma Scope actually turn a wall of numbers into something we can read? Follow the pipeline one stage at a time. Every time Gemma processes a token, each layer produces a vector of activations, a dense list of numbers. Because of superposition, those numbers are polysemantic. A single direction blends many unrelated concepts together, which is exactly why the raw activations resist any simple human interpretation on their own. Here, the sparse autoencoder goes to work. It reads those activations and re-expresses them across a much wider dictionary, forced to stay mostly zero. Gemma Scope reportedly uses a JumpReLU design, whose learnable threshold sharpens that sparsity, so only a handful of features light up for any given input. Once that expansion happens, we get interpretable features. Each one tends to be monosemantic, tracking a single recognizable concept, whether a specific idiom, a factual relation, or a step in a chain of thought. The original suite reportedly exposed tens of millions of such features spread across every layer. Now the real payoff. Because each feature is a direction we can name, researchers can inspect which ones activate, then amplify or ablate them to steer the model. Gemma Scope 2 targets exactly this: probing refusal mechanisms, chat behaviors, and chain-of-thought faithfulness inside Gemma 3. So why build a whole toolkit for this instead of just reading the neurons directly? Here's the contrast laid side by side. Reading raw neurons gets you almost nowhere. Thanks to superposition, one neuron answers to dozens of unrelated concepts, and any single concept is smeared across many neurons. You end up staring at polysemantic noise, unable to say what the network actually represents or why it made a given choice. A sparse autoencoder untangles that mess. It maps the same activations onto a sparse feature basis where each direction means one thing, so a concept lives in a place you can point to. Now you can trace which features drove an output and intervene on them, turning interpretability from guesswork into something you can actually measure. Strip it back, and three ideas make Gemma Scope matter. Openness is the whole point. DeepMind released the trained autoencoder weights publicly on Hugging Face, alongside a collab tutorial, so any researcher can load them and probe Gemma without training their own. That drops the cost of serious interpretability work from a major project to an afternoon. Coverage across every layer sets it apart. Rather than a single probe point, Gemma Scope trains autoencoders on activations throughout the network, so you can watch a concept form early and get refined deeper. Gemma Scope 2 reportedly spans the full Gemma 3 family, up to the 27 billion parameter model. Control, not just observation. Because features are named directions, you don't only read the model, you can push on it, boosting or suppressing a feature to test what it causes. That turns steering, safety probing, and refusal analysis into concrete, repeatable experiments anyone can rerun. Alright, let's lock in what matters. Gemma Scope is DeepMind's open suite of sparse autoencoders that decomposes a Gemma model's internal activations into interpretable, human-readable features. Superposition tangles many concepts into each neuron, so the autoencoder re-expresses activations across a wide, mostly zero dictionary where each surviving feature is roughly monosemantic. Because every feature is a nameable direction, researchers can inspect which ones fire, then amplify or ablate them to steer and better understand the model's behavior. This second release carries the idea to the Gemma 3 family, up to the 27 billion parameter model, for probing refusals and chain-of-thought faithfulness. Want more AI research unpacked in plain language? Come explore it with us over at standarity.com.